The last phase. The recording has begun. The lights fade away. Okay. So in any case, last part of class, since I've determined that it is physically impossible to cram more information in your heads than we have just crammed, we will just now do some problems together that relate to what we talked about. This is saving you the trouble of doing it on your own frantically the night before the midterm, as you remember that I said something about these so-called homeworks and that they were important to getting a good grade. On the video, I did air quotes in that sentence. You'll have to figure out where the air quotes were placed. So in any case, let's go over that. The way you find those things. So you can see here on the schedule, we've actually done the intro. We've done, I say processes chapter 3, 4, 5, 6, but we've skipped over kind of some of the more practical chapters. I'm doing a lot of air quoting because I'm tired. And we've skipped over some of those because we will come back to those when we do relevant projects that are relevant. So you don't have to read those, like how does the API of fork and exec exactly work? And that's one of these chapters. And then we started talking about scheduling. In fact, we just concluded by really talking about chapter 7, which you can think of as an intro to scheduling. And for some of you, you're like, oh, that's where the book is. So yeah, you can just click on these little numbers, or you can just click on this link called book. Book is all about the book, and here are the chapters of the book. And I've added a new link for people. Just some people want to donate money, apparently, to support the book. So you can click here, and it goes right to my PayPal account, which is fabulous. This is part of. I actually formed a company around this book. It's Arpaci-Dusseau Books LLC. So you'll be donating to the company, which is again to me. So, but I appreciate it because we did it for free, quote unquote. But we still make some money. And if you're interested in why I think textbooks should be free, I've written very few blog posts, but that's one that I wrote. Or you could, like I said, buy the book. And there's some money there that goes to me, so I can make money on this, but just not enough for it to be there. Of course, what you should never do when you're doing something because you want to is calculate how much time you put in and how much money you made, because then you realize you're definitely not doing it for money. And that's true of all textbooks, actually. Yeah. Can you donate Bitcoins? Well, that's a great question. Now, he's just asking that to make a joke, but sure, probably. I don't know if you can through PayPal, though. But if someone wants to give me Bitcoins, who am I to turn that down? Because, they're quite valuable, apparently. What's the current Bitcoin value? Someone's like 90, 150. I just lost my house on this. So who has Bitcoins? Okay, who made like some money on the crazed Bitcoin going up? Did anyone make a serious amount of money? A few of you. All right, so these are the people you should look at and ask for they should be sponsoring activities in here, like pizza night. So anyway, sure. But please, anyway. So let's not get off topic. I was wondering, like, how long in the class before you start talking about Bitcoin? Answer, second lecture. Or virtual sixth lecture, whatever. Okay. So back to homeworks. A lot of the chapters have homeworks at the end, and we will go over some of them. And those homeworks are often, there's two flavors. Some are just go and write some code on your own. I won't cover those as much because we kind of do projects that supplant those. And others are running little simulators. Simulations are a very powerful way to learn about computer systems. Basically, a simulator is a simplified form of, say, the thing that you're studying, like a CPU scheduler. We'll build different simulators of different CPU scheduling policies. We'll give them different workloads, in other words, different sets of jobs to run and so forth and so on. And we will see, oh, does this one have a better turnaround time than that one? And so we will be able to use these simulators as a way to make sure we're understanding the concepts of class. I'm just going to do a couple of these pretty quickly, and then we'll be done. But we'll just do a couple of problems together. This will show you how to do it on your own. But like I said, we'll use class time for this a bit because I think it's nice just to have something else to do other than me talking the whole time. So where to find these homeworks? Well, you could just, for example, look at the chapters themselves. This one's hard to see, but this is chapter 7. If you read this chapter, you'll get a lot of the things that we just talked about with better examples, and as opposed to ones that I'm probably the same ones. You wonder how much of a robot you are when you like think you're making up an example and you make up the same example every year or two that you teach this class, and then you realize, or you respond. Have you ever done this when you respond to some question? You think it's the first time you're saying anything, and someone's like, "Yeah, that's exactly what you said 3 months ago when we were talking about this." It makes you wonder about how much free will you really have. Anyway, that's a different topic on the nature of free will and whether it exists. What we're talking about now is homework for OS class, and you can see here at the end of this chapter, there's a little thing called homework, and it says, hey, there's a program called scheduler.py. It's a little Python script, and then it basically says, gives you some questions which basically force you to run the little scheduler program in a bunch of different configurations and compute the types of things that we just computed. So let's just go ahead and then there's another place you can find these. There's a homework link off the class page, which is just here. And you can see here it does basically for all the chapters that have homeworks. And the goal is, that's the last thing that I really have to do for this book is create just like a handful more homeworks for a few chapters that don't have any. But you can see here it says, scheduling basics. It says the relevant chapter is this, which is what we just linked to. And then it says, here's the program you can download and run in order to test this out on your own. Okay? So, and then there's one for the process intro part of class as well. Maybe we'll look at that too. And so why don't we just look at these two tonight? We can do it in any order, so why don't we start with this one since we were just talking about it. So I'll click on that. You can't quite see it here, but it's downloaded a little thing called homework-scheduler.tgz. How many people know what .tgz stands for in Unix systems? A few of you. So what is it? Yeah, it's like a tar and gzipped set of files. So tar is an archiving format where you can take a bunch of files and basically make them into one file, and then untar will unpack them and give you a bunch of files. And then gz is, of course, gzipped. So it's tarred and gzipped, which means it's compressed after you made it into one file. So let's go ahead and figure out how to deal with this thing. So let's say I know that it's in my downloads folder because this is a Mac, and I know it's called homework something, homework-scheduler.tgz, and then I give tar some magic flags. Of course, you can, again, people are always asking me which man pages should I read next, and so to those of you who asked that question, the tar man page is a lot of fun. You can see it's got a lot of stuff to learn, pages of stuff. There is just so much to know in the world, including like all these bizarrely useful flags that you can pass to bizarre utilities that make you actually more efficient. And you can see there's some security concerns. You might want to read those with tar. So lots of things to worry about. Anyway, it goes on. It goes on. There are alternative long options for many of the short options that are deliberately not documented. The dramatic conclusion of the tar man page. Okay, October 12th, 2009. So in any case, I don't know all those options. That's not the right thing. But what I do know is if I do tar xvzf, it'll unpack the archive and it'll do it verbosely and it'll unzip it and kind of do everything that I want. And like I said, I wanted it to be in my downloads and that. So I will go ahead and do that. And you can see I get a few things, including some files that I don't want. But if I just do an ls, I'll see these two things. In all of these homeworks, there's always a README. I had originally included the README in the book chapters, but then I was printing out 2 pages at the end of any chapter that just told you how to run a simulator. So I moved all that to just do these READMEs so that the simulators aren't described in the book per se. They're just described here. So this is worth reading if you want to understand how to run the scheduler, but I'm just going to show you right now. And as I said, this is a simulator. It's not a full system. Simulations are very useful because you can kind of get to the essence of some problem that you're interested in and study that without having to write a whole operating system. Of course, the best way to study operating system schedulers is to build an operating system, build a scheduler, run real workloads on it, and see how it behaves. But that's very complicated and takes a long time. So what you can do with little simulations is essentially build the essence of that piece, like something that switches between jobs based on some scheduling policy, and study how different things behave. So let's go and try to answer the questions that are asked at the end of the chapter of scheduling basics. And like I said, I'm just going to go over this pretty quickly, and you can do the rest on your own. So I'll go to the end of this chapter, and what we can see here is it says, first, let's run 3 jobs with length 200 and a couple different schedulers. And this isn't going to be too interesting because we basically already did this, but let's just show how to do it. So scheduler.py, and we can always ask for the help flag here, and you can see a few different options. One thing we can do is we can actually pass it a list of jobs, which are a comma-separated list of job runtimes. Most of these homeworks will either allow you to like pass in a specific workload or ask it to create like a random workload. The random workloads are useful if you want to kind of quiz yourself. It's like a way of generating an infinite number of questions about scheduling policies. I'm sure you'll spend a lot of time with that. You may spend a little though, and that's the idea. So here I'm just going to say, let's say we have 3 jobs of length 200. And then let's say the policy we're going to use is FIFO, and I don't think anything else matters. So in the world. So, so there's one other flavor of these homeworks, which is they kind of state the problem when you run it, and they say, hey, there's these 3 jobs, and so compute the turnaround time and the response time and whatever. And we didn't talk about it yet, but wait time is just how long they spend waiting in total. Or you can have the scheduler, the simulator, do it for you by giving a -c or -compute flag. So if you do -c, what it'll do is it'll basically run the simulation and then tell you what happened. It says, hey, oh, I ran, job 0 for 200 seconds, then I ran job 1 for 200 seconds, and ran job 2 for 200 seconds, and they all finished at these times. And here are the response times, here are the turnaround times, here are the averages of all those things. So you can see how it's like allows you to kind of quiz yourself and compute these things for you and see if you're doing it right. Because in the end, when we're asking you questions about these things on a midterm, it has to be these kind of quantitative questions like this, as opposed to your feelings about round-robin scheduling or the nature of free will. So, so in any case, let's do maybe a more interesting question. So now do the same, but jobs of different lengths. Okay, this is going to be pretty basic. So let's say we have jobs 300, 200, 100, and we do it with FIFO, for example. What's going to be the average turnaround time of this, this situation? FIFO, 300, 200, and then 100. Interesting guesses. All right, what we do is either we figure it out. Actually, why don't you do this? Just spend 1 minute and figure out, so you know with certainty, what is the average turnaround time and average response time of this workload with FIFO. Yeah, they'll be like, usually there's like a page or something. Yeah. We'll talk about that more. All right, why don't we just solve this by me hitting the magic button of return and let the computer do the work? Isn't that what we always like, the computer doing the work? It's what attracted us to the field. Something else can do the work for us. So we can see that one finished at 300, one finished at 500, one finished at 600. We can get the averages of that. We can get the average response time. Hopefully that matches what you got. Let's now switch the policy to shortest job first. And now, once again, compute the average, let's just do average turnaround time of our shortest job first version of this. So spend 30 seconds doing that and your usual murmur thinking as it happens. See, murmur thinking. Apparently is how people think. Okay, let's find the answer again, and then we'll ask a more conceptual question. Okay, so that's that. So all sorts of things you can do like that. You can also just run it with random, kind of random jobs. So it tells you, hey, I picked 3 jobs. Here's the 3 lengths. You can give it different random seeds, so it gives you a different question. 6, 5, and 6, or you can search the random seeds to try to get an easy question. Uh, see if you can quickly get one with all the same lengths. This would take a long time. We're not going to do it. So then we make a while loop. No, okay. So strangely, the things you will do once you have the simulator, and the computer doesn't mind. It just keeps running. It's like, what are you doing this for? It doesn't ask you. It just does it. So you can ask yourself questions like that, and you can switch the policies and so forth and so on. And there's a few other, a little bit more conceptual questions, like for what types of workloads does SJF deliver the same turnaround time as FIFO? So when do they behave similarly? Okay, so any intuitions here? When does SJF behave similarly to FIFO, or vice versa, really? When do they end up producing the same schedule? Yeah, if they all have 0 turnaround time, so they have no runtime at all. That's true. Yeah. Or a slight generalization is that they have the same run times, right? If they all have the same run times, or if in fact, if there's just a case where you generate the same schedule, right? Any place where you generate the same schedule, then FIFO will behave the same as SJF. So lots of cases like that. Are there answers to all these questions? Actually, no, there aren't. They're just, there are, but like you'd have to ask me the answer. There's no answer sheet. There's no cheat sheet floating around. But mostly the simulator helps you solve all the answer. The simulators give the answers for most of the questions that are quantitative, and then the qualitative ones you just have to think about. So we'll kind of leave that one at that. Let's look at one more of these, and then we'll call it a day. The other one we'll look at is at the end of the process intro chapter. It's called process run. This is even more simple. And then let's look at the chapter itself. So this chapter introduces the abstraction of the process. And by the way, the chapters are structured a certain way, and this is intentional. Each chapter tries to solve kind of one main problem, which we kind of call out, like what's the crux or the heart of the problem, and then build towards answering that. The reason we call that out is like in systems, if you're not careful with computer systems, it becomes just like a bunch of stuff that systems do without any real problem that you're solving. So what we're trying to do here carefully is say, look, there's always a conceptual problem we're solving, and let's try to be cognizant of that so that we think about good ways to solve that problem and see if we got to the solution. So that's kind of called out in the text in these little boxes, so make sure you understand the problem. Many times, if you simply understand the problem, you'll be able to derive the solution. It's knowing the problem is the hard part. Sometimes knowing the solution is the hard part. We'll talk about those things too. So, and then there's a bunch of other things, just if at some point you're thinking about reading along with the text, there are like some tips of things that are useful in building systems, like separating policy from mechanism. There are some poorly drawn diagrams. What can you expect from a free book? There are more diagrams that are poorly drawn. There are sometimes like depictions of behavior over time. We try to use a lot of timelines to show what's going on in a system over time as a way of understanding it. And then, like I said, there's occasional code snippets from things and other asides. So last homework here is called process run. So let's see what that's all about. I downloaded it a moment ago. XVCF, that, and then what? That. Oh, maybe make a new directory. Let's call it that. Let's do that. Okay, and then we can see the README here. And what this does is basically go through the different states of a running process like we talked about. Remember we said processes could be running, which they're on the CPU, or they could be ready to run, or they could be waiting for I/O, or of course they could be done. And then what this allows you to do is kind of play around with some different aspects of that to get a sense of how a scheduler might overlap different runs of processes in order to best utilize the CPU, for example. So let's go ahead and just look at the first question and we'll see what's what. So it tells you to run process run .py with certain flags, -L, 5100, 5100. So let's figure out what that means. Help. So the -L flag for this homework is a comma-separated list of processes to run in the form x1, y1, colon-separated, comma, x2, y2, where x is the number of instruction, kind of like CPU things that it does, instructions the process should run, and y the chances from 0 to 100% that an instruction will either use the CPU, so 100% means 100% of the time it uses the CPU, or sorry, 0 means that, well, I forget which it is actually. One of those, one of them, so when it's 100% means it's either only using the CPU or it's 100% issuing IOs all the time, and 0 is the opposite. We'll find out by running it. So I forgot which. I just ran this earlier today. So this is, each process runs for 5 like CPU units, 5 time units total, and then it has a 100% chance, I think, of doing just the CPU instruction. So let's see if that's true. And this, oh yes, it is. So this tells you what each process does. It just like, oh, I need the CPU, then I need the CPU for a tick, and then I need the CPU, and I do that 5 times. And same for process 1. And so then what we can, again, have the simulator solve this problem for us by typing -C, and then -P prints some extra statistics that might be useful. And so you can see what happened here when we ran this simulator. Let me just do that. We say basically this is a timeline of what happened. And so process 0 ran for 5 time units first, and then it was finished, and then on process 1 ran on the CPU for the 5 time units after that. And you can see the CPU was busy the entire time, and that we didn't have any I/O, so there was no, the disk was essentially never busy. Okay, so that makes sense? Kind of simple. So let's see how to make it slightly more interesting. So now it says run this. Let's paste that over here. So what is this job gonna? What is this 2 jobs gonna look like? What is this workload? Now that you know the format. Well, let's actually just look at it. So it says basically we have process 0, and it kind of wants to do 4 CPU things. So use a CPU, then use a CPU, use a CPU, CPU. And then process 1 just does one thing. It issues an I/O, and then it waits for it to complete. So when we run these, we have this kind of interesting thing that happens, which is the CPU no longer is fully busy. Why is that? Well, the CPU isn't busy because process 1 runs second, and then it just immediately issues an I/O. The I/O takes a while, and then when that I/O is done, the process can finally end. Make sense? So we see that a CPU-bound job ran first, then an I/O-bound job ran second, and we didn't get any good overlap. Now, what's going to happen? Okay, this is the one to talk with your friends about. I mean, not outside of this class. Actually, never mention this outside of class if you want to retain them as friends. But what you should talk about now with your friends in class is, what if I switch the order of these and run, that I/O-bound job first, and then the CPU-bound one next? What could be different about that? Satisfied murmur. All right. Murmuring complete. Okay, so what is going to happen? Somebody tell me. What were you talking about? Like, not class. It's almost time to get out of here. What's going to happen when we run this job that does I/O first and then the CPU bound one is kind of what's second in order here? What do we think might happen? Yeah.
There'll be overlap.
Yeah, we think they might be overlapped, right? That the I/O gets issued and then we run the other one. And so as we can see here, what happens is we run the I/O job. The I/O job then is immediately kind of switched to a waiting mode, so it's no longer runnable. And then the job that was the second job, which is CPU bound, immediately starts running. It uses the CPU, and you can see our CPU utilization goes up quite a bit. And you can see the total time for finishing those two tasks improves. So now there's a lot of different flags that you can use to kind of play around with this. The questions lead you through the different flags. For example, there is this, there's like a process switch behavior. You can easily either switch on I/O, which is what we did. So when an I/O was issued, we immediately didn't wait around. We switched to something else. We could just only switch at the end when the process is done running. So if we did that, for example, switch behavior is switch on end, then we wouldn't get this satisfying overlap because we waited until that process was done, even though it was waiting for I/O. We can look at help again, and we can change, for example, things like the I/O length. So we can play around with what happens when I/Os get slower. I/Os, of course, are very slow. So if we do switch on end and like a very long I/O time, then, then we'll be here for a while. But your point is that Python simulators don't run that fast. And of course, this is not that interesting. But I'm going to leave it running because it's kind of disturbing. It's a little unsettling that the computer program isn't going to be finished by the end of class. Or is it? We don't know. That's how the class will end today in this mystery. So those are homeworks. We'll do some in class. You're encouraged to look at them on your own. Look for two things from me in the nearby email. One is the release of the next project. And two is the creation of Piazza. Woo! Yeah. Appropriate.